Let's look at our third manner in which we can experience a force due to a magnetic field. And so this is going to be the force between two current elements. So in order to investigate this, let's consider two circuits that are operating near one another. So this circuit on the left, let's call this circuit 1, and over here on the right we have circuit 2. And so of course these aren't really complicated circuits or anything. I've just got some battery with a given polarity, and that's going to be causing a current to flow through whatever elements we have. We're not really worried about that. We're just interested in the fact that we have some currents flowing. So for our circuit 1 on the left, we're going to have some current I1, which is flowing counterclockwise. And in the circuit on the right, circuit number 2, we're going to have some current I2, which is flowing clockwise as shown here. So what we want to do in terms of figuring out the force that these two circuits exert on one another is start by considering some differential current element on each circuit. So let's say over here on circuit 1, we want to consider this little differential current element. So that's going to be I1 times DL1. And we can choose any arbitrary differential current over here on circuit 2. And so let's say this is going to be our I2 times DL2. And so the basic idea of what we're going to do here is we're going to sort of apply this to our previous case, case 2, where we said if we know our current is in the presence of some B, we can figure out our force. Well, we don't necessarily know the B, but if we go back from Biot-Savart's law in the previous unit, we know, for instance, that this differential current is going to be producing some magnetic field. So we're kind of going to take this in two steps. So let's start by saying what we want to find. So let's say, just arbitrarily, we want to find the force on our left circuit, and in particular, that differential element, differential current. So we want to find the force on our element, I1 DL1, due to that other differential element in circuit 2. So due to the field produced by our I2 DL2. Okay, so in general we know that our force is going to be related to our IDL cross B. So in this case we're talking about our current I1, so we have this current I1 DL1, and in general again it's going to be crossed with B. However, because we're considering some differential element of circuit 2, that's going to be producing some differential magnetic field dB as opposed to the full magnetic field that we would get if we integrate around the whole circuit. And of course we'll get to that eventually. But for the time being, let's just leave that as dB2, where B2 is our magnetic field produced by this differential current I2DL2. Now, because we have this extra D over here, that means we're going to need an extra differential term or an extra derivative for our force. So we no longer just have dF1, but now we have the derivative of dF1. So it's sort of like a double differential there, or double differential. And so we can note that this is of course going to depend on the distance. So let's go ahead and draw what that distance is. And actually, maybe let's go ahead and start with writing the equation explicitly. So as I mentioned, we're going to go back to our Biot-Savart's law. So our Biot-Savart's law. And so this was also on page 299 from our previous unit. And so we're going to adjust it a little bit because, of course, here we're interested in our magnetic field B as opposed to our magnetic field intensity H, which we looked at previously. And the only difference is we have to put our permeability up here in the numerator. So we have mu naught because we're talking about free space at the moment. We have current I2 DL2, so that's our differential current, crossed with a unit vector in the direction from 2 to 1, divided by 4 pi times the magnitude of that distance between 2 to 1 squared. So now we clearly see that we need that distance vector or a unit vector in that direction as well as the magnitude of that distance. So let's come back up to our figure here and let's define that vector clearly here. So this is going to be our vector R2, 1, so starting at 2, ending at 1. And so of course we could figure out the magnitude and the unit vector in that direction. Let's also, while we're looking at that sort of distance between the two, talk about the direction of this force here. So we know in general that it's going to be I1 cross B2. And so from right-hand rule, if we put our thumb in the direction of our current, in particular this differential current, I2 dl2, we see that our fingers are coming out of the page, curling towards us at this point over here. And so what that tells us then is if our dl is in this direction for our dl1, again, we use our right-hand rule, we put our fingers in the direction of dl. We're going to cross product with B, so we're curling them up towards B, which is pointing out of the page, and we see that our resultant force is going to be in the direction of our thumb, which is towards the right. So all that to say that we can know the direction of our force is going to be in this direction here. So this is our dF1, okay? And so what that's telling us is that our circuits are being pulled towards each other, or rather our circuit 1 is being pulled towards circuit 2. So coming back to our equations here, what we can see we need to do now is we need to take this expression for dB2 and just substitute it into this previous expression here. Then we're going to have these two sort of differentials out front to worry about, so what we want to do is integrate twice to get rid of that. And so doing that, we'll end up with an expression for our force. So we can say that our force 1, which is going to be the force on 1 due to 2, and I'll write that out explicitly in a minute, is equal to, and we're going to pull a lot of stuff out front. So there are a lot of constants in here. We have our I1, our I2, our mu naught, our 4 pi. So all of these are constants. So we're going to pull all of that out front. We can say this is mu naught times I1 times I2 divided by 4 pi. And now we have a double integral, both around closed paths. The first integral is going to be around our L1 circuit on the left, and the second is around our L2 circuit on the right. And now we have the remaining terms that were not pulled out. So we're going to have our dL1 from that top equation, which is going to be crossed with our dB2, but now our dB2 is going to be this term here after we've removed those constants. So that's going to be crossed with our dL2, which is crossed with our unit vector in the R21 direction. And we're dividing that then by the magnitude of R21 squared. And so of course we saw a slightly different version of this Biot-Savart's law where we had the vector R21 divided by the magnitude of that distance R21 cubed. So same thing, just slightly different way of writing it. Okay, and so again, this is going to give us the force on circuit 1 due to or from circuit 2 above. And so as we said earlier, it's going to be pulling, circuit 2 is going to be pulling circuit 1 in this direction towards the right. So it's pulling together, and that's because the currents are in the orientation as shown. So of course we would expect that to be different if our current directions were defined differently. So we can go through the same definition again, or not the same definition, but the same procedure again if we wanted to find the force on 2 due to 1. But what we can see rather easily, instead of going through that whole process, is that our F2 is just going to be equal to negative F1. So this is going to be our force on 2 from circuit 1. And so the reason that makes sense is, well, a couple of reasons. One is if we look at our cross product in this term up here, we're essentially just going to be switching the order. So now instead of doing, we're basically just switching the order there, right? So we have, instead of our dL2 in this term right here, we're going to have our dL1 cross the unit vector, and our unit vector is now going in the opposite direction. So it's going from 1 to 2. So it's going to be going in this direction. And we're also switching, now we have this is going to be I2 times dL2. And so another argument for this is, of course, Newton's third law. So we know that for every force there should be an equal and an opposite force. And so if we have our F2 pulling in one direction, we should have some opposite force pulling in the other direction as well. So not necessarily force, I should say equal and opposite. For every action, there's an equal and opposite reaction.